Matrices, and we're going to start talking about how we can use matrices to solve systems of linear equations. Let's first start talking about what a matrix is. So a matrix is just a rectangular array of real numbers. What's happening out there? Array isn't that fancy of a word, it just stands for arrangement. So it's just an arrangement . It's just a square arrangement of numbers. That's all a matrix is. It looks just like an Excel document or anything like that. The two important things about a matrix are that it has rows and it has columns. And it's important to distinguish which is which because it's going to tell you what the size of your matrix is. We're going to do different row operations, and we have to just know which is column and which is row. So when I'm given a matrix, all of these that are listed over here are our rows. So rows are the ones that go this direction. Okay, those are our rows. Those are our rows. And so in fact we have 3 rows. So it's important to mark that I have 3 rows. Alright, I said we have rows and columns. If I already named the rows, that must mean the other ones are our columns. So these guys are our columns. And we have 1, 2, 3, 4, 5 of those guys. So columns, I'm just counting how many things come down like this. Those guys are our columns. Now it's not too important now, but it's going to be important when we add, multiply, and stuff, how big our matrix is. And so whenever we name the size of a matrix, we always say rows by columns. So the size of this matrix is going to be a 3 by 5. So we always name our rows first. So 3 is our rows, always our row, and then we list how many columns we have. Put too many humps all in one thing. There we go. Okay, so we have rows and we have columns. We're supposed to determine the size of each of these matrices. Who wants to tell me the size of that first matrix? Yeah, Chris.
1 by 3.
It is 1 by 3. We have 1 row and we have 3 columns. Who can give me the size of the second one? Yeah. It's going to be a 3 by 1. And the third one? Jack?
2 by 2.
2 by 2. Awesome. And what's the size of the last one? Lewis?
3 by 2.
It's going to be a 3 by 2. Yep. Not terribly important today, but it's going to be important when we start multiplying and dividing and adding, because just knowing the size is going to let us know whether we can do a certain operation or we can't. So it's going to be important later on. What's more important today is we're going to talk about augmented matrices or an augmented matrix. We need to use an augmented matrix in order to solve linear equations. So this is an example of an augmented matrix. Notice this extra column here, right? We put this line here, and so these must be important. And if you look at what is represented by this matrix, our leading coefficients. So notice we don't have any x's or y's in our matrix. That's going to be pretty traditional that we just have numbers in there. That this is A, C, B, D. So everything that's on this side of our matrix are going to be coefficients. These are our coefficients. What goes on the opposite side is basically whatever's on the other side of the equal sign. And those are always going to be constants, because whenever we put our system of linear equations into a matrix, it's always going to be in this form where we have all of our variables on one side and just the number on the other side. So we'll always do that first, and we'll put it in this. So these will always be our constants, whatever's on the other side of that equal sign, which is going to be our constants. All right, we're going to write the augmented matrix for each of these systems, and we're going to go vice versa. So first of all, we're given two systems. We're given two systems equation. We got x equals y plus 3. We have y equals 4 minus x. And note that big note. We first have to rewrite these. We have to rewrite them so basically our variables are in order, and we have the constant on the other side. Right now I have variables on both sides, and I have y above x. So we're just going to rewrite them before we put it into our actual augmented matrix. So I'm going to rewrite this so I have my x first minus y equals 3. So I threw my y on this side and I put it after the x because that's the most traditional place for it. Alright, likewise, since I have x first, I'm going to want x first on this one. So we're going to have x plus y equals 4. So we just rewrite them. So our variables are all in order, and we just have a constant on the other side. Now we can go ahead and put it into the matrix. So the first part of our matrix are our leading coefficients. So our coefficients are our coefficients. This is our leading coefficient. Our leading coefficient is 1, and then we have negative 1. So we have basically what our matrix is saying. I have 1x, I have negative 1y, and this kind of acts as our equal sign. And then we have 3 on the other side. That's our constant. For that bottom equation, I have 1x, I have a positive 1y, and we have 4 on the other side of that equation. And that's it. Note that I don't have any x's and y's here. Do not put 1x minus 1y and 1x and 1y. Don't put x's and y's in there. All right, for the next one, we have things pretty much in order, except the big thing about this one is I'm missing something from that second one. Notice this is x plus y, and I got z. I just have an x and z here. How many y's do I have in that second equation? Yeah.
0.
I have 0 of them. So there's a couple ways to account for that. I'm not going to do this way very often because it takes a while. You can rewrite everything. So I can rewrite x plus 2y minus z equals 1. And I can have 2x plus, just like Chris said, I have 0y plus 3z equals 5. And 3x minus 2y plus z equals 0. This is kind of a tedious way to do it, primarily because I had to rewrite all of this just to put 0y in there. I think an easier way to do that than doing that every single time is to go ahead and start your matrix and just tell yourself, hey, I have an x value, I have a y value, and a z value. So you can just go right above and just say, well, what are my x values, what are my y values, and what are my z values? And then we have equal, and then our constants are on the other side. That way you don't lose values along the way. It also helps you if you didn't rewrite this in the proper order. All right, I can just look through this thing and say, well, I have 1x in this top one, so under my x column I'd put 1. On my next column I have 2 x's, so we put 2 there. Bottom one I have 3 x's, so I can put a 3 there. For my top one I have 2 y's, so I'll put a 2 on top. My second one I have no y's, so either I can just see it there, or I can look over here. Either way, I have 0 y's. In that bottom equation, I have negative 2 of them. For my z's, I have negative 1 for that top one. I have 3 for that second equation, and for the bottom, I have 1. And finally, our coefficients are 1, 5, and 0. Not our coefficients, but our constants. And that is now in matrix form. All right, let's go the other way. So we're supposed to write the systems for each augmented matrix. I want to make a note on this guy right here. This is what's called the identity, and we'll talk a little bit more about it in a second. It is a very key thing to know about matrices. In fact, knowing what an identity is going to be crucial to be able to solve these systems equations using matrix. So if we look at that identity, we're going to notice that I have rewriting this as equations, it'd be 1x plus 0 y's equals 5. And here I'd have 0 y's plus, or 0 x's, sorry. 0 x's plus 1 y, and let's just call it y. And that's going to equal 1. Well, if I rewrite this, or I wrote it the other way to begin with, we would just see we have x equals 5 and y equals 1. So if we're in the identity form, we know what all our variables equal. All right, so if I note that's an identity, and we'll talk a little more about it in a second, but when I have that diagonal 1s in each column, I know what x equals and I know what y equals, and I no longer have a system of equations. Instead, I have a solution. I have x equals 5 and y equals 1. All right, let's go through this guy here. All right, so sometimes it's nice to label what you're going to use. Well, I'm going to use x, y, and z. So going across, I just have 2 x's. I have 3 y's, and it's a positive 3, plus 4z equals 6. Going down, I have negative x plus 0y. For now, I'm going to write that in there. Plus 5z equals negative 2. And finally, our final one is I just have 1x minus 2y plus 3z equals 1. All right, if I ask you to do this on a test, and you're concerned about this, don't be concerned about this. All right? Writing 0y, although redundant, is still correct, because you technically have 0 y's. However, if you're someone that doesn't like having it there, you can just leave it out. You can just have that negative x plus 5y. In fact, you could write this negative x over here. All 3 of these are valid ways, and the book uses all 3 ways. So you can have just negative x and leave a blank here and have the plus z. You could slide this over, or you could have 0y in its place. All 3 are completely correct, 100% used across the board. All right, this space is sometimes nice, because if you have to rewrite it, you already know you have that missing area. But I think more traditionally, you just bump this over and just have negative x plus 5z and not worry about a space there. All right, so don't worry about if you have 0y, you can either write it or not write it. It's up to you.
What if like the whole entire row is 0?
What if the whole entire row is 0? So I think I know what you mean. So let's say, and we're going to talk a little bit about this tomorrow, but we can talk about it now. Like that?
Like, yeah, like everything.
Even the 1?
Yeah. Like, not to say I was looking at the homework, but it's on the homework. I was like, would you just like leave it blank?
So if it's like this, not saying you're looking at the homework, but it's on the homework.
Yeah.
No, you wouldn't say it's blank. You would actually say, because pretend this is an equal sign, right?
Yeah.
What if I had 0 plus 0 plus 0? You'd have 0 equals 0.
Oh.
So if that whole row was just zeros, and it's going to be a special case, and we're going to talk more about it tomorrow, but you would honestly have, if you came up with 0, 0, 0, you come up with 0 equals 0.
So you would get it wrong if you just like did it.
If you just...
Okay.
All right, we're kind of getting into tomorrow's territory,
Yeah,
but that's okay. That's okay. When I solve a system of equations, like using substitution, elimination, and I drop my variables and I come up with a true statement, how many solutions are there? Like if I come up with a 6 equals 6, 2 equals 2, yeah, an infinite number of solutions. So in fact, this is going to be the same thing. We're going to have an infinite number of solutions because one of ours dropped down and came to 0 equals 0, which is true. There's going to be times where it's 0, 0, 0, 0, 6, and you have 0 equals 6, which means there's no solutions. And we'll talk more about that tomorrow, but I'm glad you brought that up. So you can't just forget about it. You can't be like, meh, don't need you. Okay, yeah. Good question. Good insight. All right, when we're solving systems of linear equations using matrices, we have to use row operation. We have to have a way to manipulate it, because I can't just look at it and know the answer. Just like when I give you a system equation, you use substitution, elimination, and you could graph it. Our row operations are going to let us get from point A to point B and actually manipulate our matrix to how I want it to look. So we can do 3 different things to matrices. Well, right now we're going to do 3. We can interchange 2 rows, and I'll show you the example real quick, which means we can flip them. We can multiply every element in a row by a non-zero real number. Obviously, we don't want to multiply it by 0, because that's like multiplying both sides of an equation by 0. We don't do that. Can't do it here. We can also add 1 row to another row. All right, let's see those 3 examples and kind of how I write it. So we can interchange 2 rows. That means I'm just going to flip the 2 rows. So if I have 2, 4, 8 on top, we're just going to put it on bottom. So we're just going to flip the location of both of these things. And then it'll be 2, 4, and 8. And kind of how this makes sense is if I give you 2 linear equations and you write them upside, like, let's just show an example real quick. So if I gave you these 2 linear equations and then you wrote them this direction, would that change solving them? No. That's the same thing you're doing with matrix. All right, you're just rewriting them in a different place. Your answer is going to be the same. All right, the second thing is you can multiply every row in an element by a number as long as it's non-zero. Just like when you're dealing with if I have 2x plus 4y equals 6, I can multiply both sides by 3 as long as I do it to both sides. Ooh, real quick. Notation. Usually when I flip them, I don't usually write it, which not good practice. But you do need to tell your reader what you did. Because when you're doing row operations, a lot of times you're not actually showing the math behind it. You're doing a lot of it in your head or on scratch work. So you do need to tell your reader that you flipped those 2 things and you didn't do something else. So how we're going to write that is we're going to write it as I took row 1 and I interchanged that with row 2. So that arrow right there, that double arrow, tells me I flipped them, basically. I interchanged those 2 rows. All right, for our next one, we're going to multiply every element in 1 row by a non-zero real number. So what I'm going to do is I'm going to multiply that top row by 2. So we're just going to multiply that top row by 2. Like I said, a lot of this isn't done on hand, so I'm just going to go 2 times 2 is 4. 2 times 4 is 8. 8 times 2 is 16. And I didn't do anything to the second row. Once again, I want to tell my reader, or even myself later on, what I did. So all we're going to say is I multiplied row 1 by 2. And then I replaced that 2 times R1 into R1. So I multiplied row 1 by 2, and I replaced row 1 with that 2 times R1. Oh, yeah. I just want to put on here that this just means replace. That arrow just means replace. A lot of times, this gets dropped off. All right, it starts getting chopped off because it gets kind of repetitive to write this all the time. If you say 2 times R1 and you put it right here, I know what you did. So a lot of times this gets chopped off. Let's just practice using it for right now. And when we get to more complex ones, where we're doing more steps, that's so you can start chopping it off. Just not right now. Okay, yeah?
How do you pick what number to multiply by?
We're going to find that out in a little bit. But right now, this is a dumb thing to multiply it by. Because this didn't help me at all. But we'll find out what we're gearing towards in a second. Good question. All right. The last one says add a multiple of a row to another row. So that means I can take one row and add it to another row. Okay? So, what did I do? So Alex, honestly, I just picked random things to do in here. So I didn't actually, I'm not gearing towards anything here. So I did multiply row 2 by 2 and add it to row 1. So let me write that down so you can see what I'm doing. Let's make this a little shorter because I don't have a ton of room. So I'm going to do 2 times row 2. I'm going to add it to row 1, and I'm going to put that in the place of row 1. I kind of ran out of room, but this is just 2 times row 2 plus row 1. Put it in row 1's place. Okay? So we're going to kind of do this in our head. So I'm going to multiply row 2 by 2. So let's do this element by element. So I'm going to do 2 times negative 1, which gives me negative 2. Yeah, thanks, Mike. And then I'm going to add it to row 1. What's negative 2 plus 2? 0. So I'm going to replace row 1 with 0. Let's keep going. I have 2 times 3, which gives me 6. Add that to 4, and I now have 10. My final step is 2 times 2 is 4, plus 8 is 12. And because I only replaced row 1, I didn't actually do anything to row 2. I just used it to add. So row 2 is going to stay the same. So it'll be negative 1, 3, and 2. And I'll be honest with you, a lot of this stuff is going to be tough to kind of keep straight in your head. So what oftentimes I do is either off to the side or somewhere around here. It doesn't matter where, because this is just your tool. This is a tool to solve it. What I do a lot of times, I'm doing 2 times R2, so I'll actually make a little note to myself. Hey, 2 times row 2 is negative 2, 6, and 4. Then in my head I can go negative 2 times, oh, yep, that's 0. 6 plus 4, yep, that's 10. 4 plus 8, yeah, that's 12. So it's not a bad idea, Jack, to make notes to yourself. All right, especially because at one point we're going to be doing multiple row operations at once. So it's good to have all the numbers you're working with written down somewhere. All right, how do we know what we multiply by? It is going to be guided by this thing called the Gauss-Jordan elimination method. Gauss is a very, very famous mathematician. He did lots and lots of theories that you already use. But we're not going to get into that right now. We're going to get into this awesome method he came up with. So solving a system using increasingly simpler equivalent augmented matrices. In other words, what we're going to do is we're going to take any matrix that we have and we're going to whittle it down to the identity matrix. So we're going to whittle it down to get to the identity matrix. And this guy right here is the identity matrix. The identity matrix is going to be a diagonal of 1s where everything else is zeros. Okay, so if I had a 3 by 3 matrix, I'm going to do another example. The identity matrix would be a diagonal of 1s and everything else would be zeros. That also is an identity matrix. Now there's odd identity matrices, and it's hard to get into. I'm just going to show you kind of one example. Let's say I had an additional numbers over here. This is still considered the identity matrix, even though these aren't zeros. This is still the identity matrix because I did my best to have all of these as 1s, the angles, because I can't go any further, and I have everything else that's in this little section, 1s and zeros. It's just, this can be a different type of solution. All right, so as best we can, we're going to go from left to right, making them into 1s and zeros diagonally. All right, so you can picture a 4 by 4 is going to have 1s all the way across, and we'll just have some more zeros. But you have to know what it looks like in order to know what we're actually trying to gear towards. All right, so our whole goal is take a matrix, actually take a system of equations, write it as a matrix, and then find the identity of that matrix. Yeah?
So like, say with the example we're doing next, does matrices work better when you have like, well, is that like an easier method when you have 3 equations?
Yeah, Alex brought up a great point. If I was given this, and I was given a test on this, I would probably not make a matrix. Because it's probably just easier using elimination or some other form. And we can see, I mean, it depends how good you are at matrices. Some people are really good at matrices, and they would actually do it in their head almost. All right. The good thing about matrices, can you right now plug this in your calculator and it solves it for you? You can? You can write it. Oh. So you can't type in 2x minus 4y equals 16, 3x plus y equals 3. However, your calculator has this awesome matrix function. And it's got this reduced row echelon form that will actually, if you plug this in using the matrix, we're not using it today. We're using it tomorrow. You could plug in your calculator pops out an answer for you. But you have to understand how to interpret the answer. Okay? So that's the good thing about matrices. You can now use your calculator as of tomorrow. Today we're going to stick with. In fact, we're not even doing much matrices in your homework. Most of it is just, this is a backbone of tomorrow. All right, so we're supposed to solve this equation. We're supposed to use matrices. So the first thing I'm going to do is I'm going to write it as an augmented matrix. And I do apologize for people in the back. It's going to get a little low. So just be ready to stand or peer over. Okay, so the first thing I'm going to do is I'm going to make an augmented matrix. The first thing I'm going to do is I'm going to make sure my x's and y's are lined up. Yep. I don't have any z's, so I don't have to worry about any zeros. Everything's lined up, so we're going to go ahead and make our augmented matrix. So that means I have 2 x's. I have negative 4 y's. 16. And then we have 3, 1, and 3. All right, the book has like 9 steps on how to do this. I break it down to just these steps here. First key is you have to work from left to right. We start on the very left, and we work right. Second step is locate what value is supposed to be 1. And then you're going to make it 1. Either you're going to make it 1 by multiplying, or you're going to switch rows, we'll see tomorrow, but focus on just multiplying today. After you make that 1, 1, you make all the rest of them in the column 0. Because we know this is supposed to be a diagonal with 1s and 0s everywhere else. So we start from the left. All right, we go all the way to the left, and we work at 1 column at a time. Don't try to do multiple columns at once. 1 column at a time. So I'm basically covering this up, and I'm looking at that 2 and 3. Which one needs to be 1? The 2 or the 3? Mike? The 2. The 2 needs to be 1. What can I multiply 2 by to make it 1? It's a tough one. It's a toughie, yeah. Multiply by half. So I'm just looking at, well, if I multiply 2 by half, I'm good. So we're just going to multiply this whole top by 1/2. Okay, and how that's going to look is I'm just going to write a new matrix. Try to make it a little smaller so I don't have to run too far down. And I'm going to tell myself I'm going to multiply the top row, row 1, by 1/2. And like I said, we're going to replace row 1 with that 1/2. All right, 2 times 1/2 is 1. Yay. So we did what we wanted to. We turned that into 1. Negative 4 is negative 2. And 16 times 1/2 is 8. I didn't do anything to the bottom row, so that's 3, 1, 3. All right, now we need to make this value 0. So we're working on 1 column at a time, so we need to make that 3 a 0. And what we're going to use to make that 3 a 0 is I'm going to use this 1. So once again, I forget about everything else, and I'm just looking at 1 and 3. Now I can multiply 1 by whatever I want, and I can add it to this. What can I multiply 1 by so that if I added it to this, this turns to 0, Alex? A negative 3. So if I'm multiplying this by negative 3, I'm going to multiply this whole row by negative 3, add it to this row. Okay? So in the written form, what I would always do is, a lot of times I ask myself, am I changing row 1 at all? No, I'm not changing row 1 because I just want to change this to a 0. So I'm just going to rewrite row 1. 1, negative 2, 8. Row 2, however, is going to be different because Alex told me to multiply row 1 by negative 3. And then I'm going to add it to row 2. And that's going to go in row 2's spot. All right, so we have negative 3 times 1 plus 3. That equals 0. Negative 3 times a negative 2, that's a positive 6. Yeah, Alex?
I just have a question when we're writing the notation or whatever. Because isn't row 2 like that whole, those 3 values?
Yeah.
So like, we're not doing the whole row by negative 3.
You have to do the whole row.
Oh, okay.
It's kind of like if I have like 4x plus 2y equals 4, and I say, well, I just want to multiply the x value by 2. Are you allowed to do that? No, you have to multiply the whole thing. So as soon as I do something to one part of the row, I have to do the whole thing. Does that make sense? Okay. All right, so now we're going to do negative 3 times negative 2, which is a positive 6. 6 plus 1 is going to give me 7. And finally, I have negative 3 times 8. Negative 24 plus 3 is a negative 21. All right, I'm going to come back up here for people on the... Mike, can you see it all? Okay? All right. So I'm going to move back up here. I'm just going to start drawing my augmented matrix. But we're going to think about this really quick. I'm done with this column. So now we're going to move right. My next step, as soon as I get to a new column, is figure out what value needs to be 1. What value needs to be 1 in that next column? There. It's not going to be the negative 24.
Hold on.
No, because it's negative 3 times 8, which is negative 24. Added to 3 is... Mike, do you have an answer?
Yeah.
Yeah, what?
7.
The 7 needs to be 1, so I'm just focusing on that 7. And Mike, can you also tell me what I want to multiply that whole row by to get 7 equaling 1? 1 7. Yeah, not that hard, right? Those should be the easy ones. All right, I'm not doing anything to row 1, so leave that as 1. Negative 2, 8. But like Mike said, multiply that bottom row by 1 7th, row 2, and that's going to replace my row 2. 0 times 1 7th is 0. 7 divided by, or 7 times 1 7th is going to be 1. Negative 21 is going to be negative 3. And this is why we work on one column at a time. Note that at one point we had a 1 here, right?
Yeah.
And if we just try to focus on keeping that 1, we'd have no way of getting this to being 0. All right, so we focus on one column at a time and work our way. And note now, no matter what I do to this row, this is always going to be 0. If I multiply it, divide it, this will always stay 0. All right, last thing we have to do is make that negative 2 0. Can someone give me a hint at what I have to do to make that negative 2 equal to 0? Ethan?
2 times row 2 plus row 1.
Yep, absolutely. I don't know why my matrix is getting all messed up. All right, there we go. So Ethan told me, hey, take row 2 and multiply it by 2. And add it to row 1. All right, 2 times 0 is 0, so that 1 stays. 2 times 2 is 2. Plus negative 2 is 0. 2 times negative 3 is negative 6. Plus 8 is going to give me 2. And my bottom row stays the same. 0, 1, negative 3. Now we have our answer. Remember that these are my x values and these are my y values. Well, my first one is 1x plus 0y's equals 2, so it's x equals 2. And it's y equals 1. So we can either write that or negative 3, sorry. I got ahead of myself. Negative 3, so, or we could write 2, negative 3. Either one of those are perfectly fine solutions to this. Or you can write both, just because you like to write both things. All right, like I said, you don't have to do this in the homework, really. The homework's basically, can you do row operations that they tell you to do? This is more of a start for tomorrow, because we're going to do a much more complex one tomorrow. We're going to do a 3x3, which is going to be a little rough. All right, keeping stuff track. And then we'll learn how to use our calculators for this tomorrow. All right? So let's make sure we work on our homework.